So hi guys, welcome back to our channel. Today we'll be solving an assignment method problem using the Hungarian method. The Hungarian algorithm is used in assignment problems when we want to minimize costs. This lesson will go over the steps of this algorithm, and we will also see this algorithm in action by applying it to a real-world example. So here is the problem. The Burlington Police Department has 5 detective squads available for assignment to 5 open crimes. The chief of detectives wishes to assign the squad so that the total time to conclude the cases is minimized. The average number of days based on past performance for each squad to complete each case is as follows. So the goal of this problem is to assign 5 detective squads available to 5 open crimes. It also wants to minimize the total time to conclude the cases. So to solve this problem, the first step is to apply row reduction. In row reduction, we will choose the smallest value in each row and subtract each value to all the values in their certain row. So for example, for row 1, we can see that the smallest value is 3. Therefore, we will subtract 3 to all the values in row 1. We will repeat this step until we are done with all the rows. So the right table, as we can see, is the resulting table. So the next step is to apply column reduction. In column reduction, we will choose the smallest value in each column and subtract each value to all the values in their certain column. So for example, for column 1, we can see that the smallest value is 1. Therefore, we will subtract 1 to all the values in column 1. We will repeat the step until we are done with all the columns. So the right table represents the resulting table. So after column reduction, we will now check for optimality. Since there are 5 lines and this is a 5 by 5 table, we have now arrived at our optimal solution. Since this problem wants to know who to assign to a specific case, we will now look for a solution by choosing zeros in the table. As we can see in the table, Squad 4 will be assigned to Case A. Squad 3 will be assigned to Case B. Squad 1 will be assigned to Case C. Squad 2 will be assigned to Case D. And lastly, Squad 5 will be assigned to Case E. So in order to get the total time, we will now replace the zero values with its original values from the first table. So as we can see from the table, 1C yields 3, 2D is equals to 6, 3B is equals to 3, 4A is equals to 8, and 5E is equals to 8. Since there are no other possible solutions to this problem, and by adding everything, we can get that the optimal solution is 28 days.
A trucking company has a contract to move 115 truckloads of sand per week between 3 sand washing plants W, X, and Y, and 3 destinations A, B, and C. Cost and volume information is given below. Compute the optimal transportation cost. Using northwest corner rule, here is the table. So, in plant W, project A, the demand capacity is 45 and the supply capacity is 35. So, we need to allocate 35. Next is at plant X, project A. Since we already allocated 35 and the demand capacity is 45, so we need to allocate 10. The next one is at plant X, project B. Since we already allocated 10 at plant X, project A, so since the supply capacity is at 40, so we need to allocate 30 at plant X, project B. Next is at plant Y, project B. Since we already allocated 30 in plant X, project B, we only need 20 to allocate in plant Y, project B. Next is at plant Y, project C. Since we already allocated 20 in plant Y, project B, and the supply capacity is 40, so we need to allocate 20 in plant Y project C. From plant W to project A, number of units shipped is 35 and the cost per unit is $5, so the total cost is $175. From plant X to project A, number of units shipped is 10 and the cost per unit is 20. The total cost is $200. From plant X to project B, number of units shipped is 30 and the cost per unit is 30. The total cost is $900. From plant Y to project B, number of units shipped is 20 and the cost per unit is 8, so the total cost is $160. From plant Y to project C, number of units shipped is 20 and the cost per unit is 12, so the total cost is $240. Summing up everything, the total transportation cost is $1,675.
Today we're going to try to do an example of a minimal spanning tree problem. What we need to find in minimal spanning is a tree that is able to connect all the nodes in the smallest or shortest possible way. If, for example, a cabling company would want to reduce their costs, then they would employ minimal spanning to find the minimum amount of cables that they can use. So again, the cabling company would want to know how to connect all the houses to their network by using the smallest amount of cables. So if we can take a look at this example, we can have the nodes represent the houses or buildings that need to be connected, and we have our arcs, and on the arcs are numbers, or what we can call weights, that can represent the meters of cables that need to be used. So we use something that's called Kristel's algorithm. Kristel's algorithm means that we choose the smallest weight first and then the next, as long as it improves our connectivity. So we have here our edges and our weights. So what are the edges? Are our arcs. So for the smallest one, we have here 3. So we can go ahead and connect this, and we have A to B, edge A to B, and we have a weight of 3. The next smallest edge would be from B to C, which is a 4, and we can see that there is also another value of 4 from E to F. So we can, it doesn't matter. So from B to C we have 4, and then again we have the next smallest, which is 4. So we can go and add that up. That's 4 also. Next, our smallest would be 5. So there are again 2 values of 5. So as long as it improves our connectivity, again, we can go ahead and connect that. So we have A, D, 5, and D to E is 5. So next we have the smallest value is 6. But if we put a line here, it will not improve our connectivity because it will create a small loop here. So it's going to be a bit redundant. So we are not going to include that. And now you can see that all of the nodes, all of our houses are connected to one another without actually being connected to each and every house. So we're going to end there. We're not going to look at these other edges anymore because they will be become redundant. So to sum this up, we have 3 plus 4 is 7, plus 4 is 11, plus 5 is 16, plus 5 is 21. So to see again if our connection is correct, we can see that all of the nodes are connected and there are no breaks in the tree. So our final answer here would be 21, which represents the amount of cable wire that will be needed. So that is how you solve a minimal spanning tree problem using Kruskal's algorithm. Thank you for watching.